the place we ended last time, I think we're pretty well through discussing the basics of homolytic or radical reactions, at least for now. We've gone through one example of a radical reaction, and you'll get to practice more with them. You'll get to consider the idea of what if you start the reaction with an excess of an alkane that can give multiple possible monohalogenation products. So you'll get to consider that in OWL. And just other ways of drawing these mechanisms using these half arrows or fishhook arrows. And as I've said, very few of the reactions we'll study will be radical reactions, but we will also look at some others. And it's important to know how they work so that you can understand them when they come along. So I do want to be as clear as possible. Memorizing the reaction that we went over on Monday is not going to be an adequate level of mastery. I would expect that the successful student would be able to draw a similar mechanism, starting with either bromine or chlorine and an alkane that you've never seen before. And if you're given the product, so you know where the carbon-hydrogen bond changes to carbon-halogen bond, I would expect that you would be able to draw the full mechanism like we did in class the other day. I don't know that that's an exhaustive description, but to me, that at least is something to aim for. That's what I will ask you all to aim for. That's all fine, but we need to get back now to heterolytic reactions, which I think in contrast are going to seem a lot more familiar, even to us already, because we've already looked at a bunch of heterolytic reactions, also called polar reactions. There you go again, needs to be two names for anything. My deep thought this morning was, it's better that we have two words that mean the same thing than one word that means two different things. That would be a problem. So as annoying as it is to find there to be two or three names for the exact same thing, we're going to hit it again in a moment with nucleophiles and electrophiles, I think it beats the alternative. And then the rest of the chapter is mainly a review from Gen Chem about reaction energy, reaction rate, the different types of energy, your Gibbs energy, the enthalpy or energy related to heat, entropy, which is energy of disorder, and how all that ties together. So it's something you've covered in Gen Chem. And I have a number of things that I'm going to want to remind you guys of that will also flow in very well to chapter 7, because there's more consideration of energy diagrams and all of that in chapter 7. So I would say that my plan is by the time we finish talking about, by the time we get to the place in the schedule where it says we're to be finished with chapter 7, I'm going to have said all that I've intended to say on chapters 6 and 7, since there is a great deal of overlap between chapters 6 and 7. Okay, so again, what we're going to do is start with just an example of a polar reaction. It's one that we're going to learn more about in chapter 8 when we consider addition reactions of alkenes in general. And indeed, this reaction is an addition reaction to an alkene. I'm just using ethylene. It's the simplest possible alkene, but one thing we'll learn in chapter 8 is this could be any alkene. And alkenes like to undergo electrophilic addition reactions, where the alkene acts as our Lewis base. And we'll see that when we cover the mechanism in just a few minutes. So this is going to be our nucleophile. And essentially, nucleophiles and Lewis bases are the same thing. It's, again, two sets of terms that I'm hard-pressed to tell you any difference in meaning between those two sets of terms. So a nucleophile is a Lewis base is a nucleophile. And we've already defined Lewis base. You had that defined in Gen Chem. Likewise, an electrophile is a Lewis acid, and a Lewis acid is an electrophile. I don't know why there's two sets of terms. There may be subtle differences in how professionals use them in this or that context in, say, a scholarly article, but for our purposes, I mean, I'm racking my brain. I'm having trouble coming up with any difference between those two, any significant or meaningful difference between those two sets of terms. I think you can consider them to be two sets of synonyms, and I think that will be just fine. In a typical addition reaction of alkenes, and we'll learn others besides this, the alkene is going to act as our nucleophile, as our Lewis base. And the way we know that is because there's a pi bond here, and pi electrons are more available to move and form a bond elsewhere than sigma electrons, other things being equal. In Gen Chem, you learned that electrons in a pi molecular orbital are higher in energy than electrons in a sigma molecular orbital. And we don't need to go drawing orbital diagrams. I know how much you loved that because many years ago I taught that. But you know, all that stuff is still there, as is, there's going to be a lot more like that in chapters 6 and 7, by the way. But anyway, that's just to demonstrate that the pi electrons are more available, more reactive, you can say, more labile. They're more, they have more readiness to move and to form a bond elsewhere than electrons in a sigma bond. Meanwhile, alkenes undergo addition reactions with a wide variety of electrophiles, and we'll cover all of them in chapter 8, as I said. One of these is your hydrohalic acids, with one exception. And here I'm using HCl. I could just as easily have used HCl. I could just as easily have used HBr or HI. The way I know that is all three of those are strong acids. HCl, HBr, and HI are all strong acids. They like to ionize completely in aqueous solution, for example. So you learned those in Gen Chem. And then you can also see the exception is HF. And the reason is HF is a weak acid, owing to the hydrogen-fluorine bond being exceedingly strong. So that's why HF is the odd one out. So I don't want you memorizing fluorine is always no and iodine is always no and the other two are always yes. You have to think about each different situation. It's different whether we're talking about elemental halogens like Cl2 and Br2 or hydrohalic acids like HCl and HBr. I only mention that because that sort of thing is a very common mistake that I see over the years. People try to memorize simple rules and expect them always to apply. And sometimes you can do that. Sometimes there are simple rules that just work. This is not one of them. So I think you all see the issue, right? That when I say I don't want you memorizing Cl and Br are always yes and F and I are always no. Because HI would certainly work here in place of HCl. And the way you know that is, again, HCl, HBr, and HI are very similar species. They're all strong acids, whereas HF is a weak acid. It's very strange because HF is a nasty substance to deal with. It will eat glass, for instance. And goodness knows what it would do to, you know, flesh. But be that as it may, although it is very corrosive and nasty and horrible, it is a weak acid. Again, because the hydrogen-fluorine bond is very strong. And you can verify that by looking it up in a table of bond association energies, which I, of course, don't expect you to memorize those things, but if you did, look it up. Previous teacher says it seeps through skin and eats bone. Yeah, it's bad. I mean, you do not want to get this stuff on yourself. I mean, I wouldn't want to go taking a bath in HCl, HBr, HI either. Don't get me wrong, but if I had to choose between HCl and HF, it's a clear choice. HCl you could hold in the palm, even concentrated, you could hold in the palm of your hand for a few seconds. I wouldn't say for hours, wouldn't go taking a bath in it, but you could, and I don't think it would hurt you too much. So yes, that's quite correct. It's nasty stuff. Good. So in the end, we get an addition product. And I'm only using colors and drawing it like this just to make it easier to see. Of course, the product here is just chloroethane. And you can draw chloroethane however you would like to draw chloroethane. But I'm just trying to give some clear visual aids here for how this thing works. And the mechanism of this reaction is known, and the energetics of the reaction are pretty well studied. But we're just going to use this reaction as an example of a polar reaction, of a heterolytic reaction, so that we get used to the idea of how we show these mechanisms, which again, if I had to take a guess, at least 98% of the reactions that you're going to need to know for exams this term and next term are going to be of this type, are going to be heterolytic processes. There will be a couple radical reactions here and there, but nearly all of them will be heterolytic processes. And we're getting more interesting HF discussion. Awesome. Anyway, you will forgive me for not speaking of it directly. Okay, so this mechanism is known to go in 2 steps. The first step involves our alkene pi bond acting as a Lewis base, acting as a nucleophile. And those electrons are going to reach out towards our electrophile. And how do we know where the electrophilic portion of the HCl bond is? Well, we know that chlorine is a good deal more electronegative than hydrogen, right? So hydrogen is the part of the molecule that has a partial plus charge. You could show that with a polarity arrow. We don't normally do this unless the question says to show the polarity arrows. I mean, I'm trying to get away from lecturing in those terms, but I know that a lot of students expect that. And as we make this transition into learning how to actually master material and not just, you know, memorize lists of facts, which goodness knows, that's not an easy transition to make. It's uncomfortable. But for that reason, I'm trying to address student concerns and go there occasionally, at least now at the beginning. In any case, we've got a part of the molecule that is electron rich. As we said, that pi bond includes an electron pair that's relatively high in energy, relatively more reactive than any of those 1, 2, 3, 4, 5 sigma bonds, for example. And we've got here a very polarized, a very weak bond. This bond very much wants to break and give up H+, that's the definition of an acid, right? And make also a chloride ion, Cl-. And so the arrows don't have to look exactly like this, but one way to show it is like this. We're showing that the pi bond is remaining attached to this carbon, and it's kind of swinging away, thinking in terms of cameras. I like to think of the pi bond as sort of swinging away from one atom and remaining attached to the other. And so let me see if I can maybe add some color and make that clearer what I'm talking about. The pi bond is going to remain attached over here. And it swings away from the other carbon. So this carbon is going to wind up short an electron pair. And that's going to have implications for what the intermediates are that we draw in the next step. Of course, we're not done with this. And I mean, I think we've already been over this. Of course, any reasonable variation on this is fine. You know, if you want your arrow to go underneath, that's totally fine. If you want to put your HCl in a different place and have the arrow go there to that other place, that's perfectly fine. There's any number, maybe even an infinite variety of other correct ways of drawing this. I don't want you to memorize that it looks exactly like this. That is not an adequate level of understanding. Like I said, you need to be ready for being given an alkene you've never seen before, and then this could be HCl or HF or HBr or HI. That's what you need to work towards. And goodness knows you don't know that right now. It takes practice. You're not born knowing this. I'm well aware of that. But I'm trying to give you an idea of what to aim for when you practice. It's not enough just to memorize the example we did in class. Anyway, as I said, we can't stop here because with this, we formed a bond from the carbon that the pi bond is remaining attached, or the pi electrons, I should say, are remaining attached to. Actually, let me rephrase that, in fact. Let me change that from pi bond stays attached here to pi electrons stay attached here. I think that's a little clearer. Of course, they're not going to be pi electrons for too much longer. Stay attached here. There we go. So again, think of that bond as sort of breaking away from, I'm sure it really makes that sound too, like if you listen real close, you know. But anyway, think of it as breaking away from the other carbon. It's going to leave the other carbon as electron poor, and then the electrons are going to stay attached here and form another bond to that carbon. How do you know what it's forming another bond to? Well, by the atom that this electron, that this curved arrow is pointing towards. This communicates that we're using those two electrons that were in the pi bond to make a new carbon-hydrogen bond. That's what that arrow communicates. And you have to understand what it means, not just memorize that there's an arrow somewhere. That's so important to success in organic chemistry. And again, once you see that, then you immediately understand, well, we can't stop here, because otherwise this hydrogen will have two bonds, and that's not possible. Hydrogen can form only one bond. So the sensible thing to do is to break the hydrogen-chlorine bond and put that electron pair onto the chlorine nucleus. And when we do that, you'll get a chlorine with 8 electrons around it, also known as a chloride ion. And so that's how we know what to put next. I should probably have color-coded this, but that's okay. It's okay. I'll push you a little bit. I'll challenge you somewhat. Oops. And I'm not going to draw everything all at once, but there's our chloride ion. The extra electron pair had been in the hydrogen-chlorine bond. And this carbon now has 3 hydrogens attached. 2 of them were there to begin with. 1 of them just got added. So I think you'll see this is balanced for mass. And there's one thing I'm missing. We need to do something with this carbon, because now it is only 6 electrons around it. And if you can even verify this with that formula for calculating formal charge, but a carbon with 3 bonds and no lone pairs has a charge of +1, formal charge of +1. This type of species is known as a carbocation. And the definition of a carbocation, I'll leave the definition as a picture. It's any time, not just this one, any time you have a carbon with 3 bonds and no lone pairs and a plus charge. Such a carbon is known as a carbocation. And it's a very common kind of intermediate. That's another thing we need to address today, though I'll probably have more to say when we get to chapter 7, which is the difference between an intermediate and a transition state. You talked about that in Gen Chem, and it's subtle, but they are completely different animals. And one of the things that we'll say about intermediates, such as carbocations, is that intermediates are real species. And species like this have been detected experimentally. So we know that the reaction goes through this mechanism. So we've detected carbocations experimentally, either using spectroscopy or some kind of trapping method or something like that. So this reaction is known to go through 2 steps. And again, that's regardless of the alkene and regardless of whether this is HCl, HBr, or HI. Any such reaction like this, any such hydrohalogenation, if you will, of an alkene, any reaction of that type will always go through 2 steps. The first step involves protonation of the pi bond in the alkene, and it will always look something like that, and formation of a halide ion and this carbocation. So that's going to be the first step. And when we say that there's 2 separate steps, what that means is we need to understand that all of this doesn't have, that everything we're about to draw doesn't all happen at the same time. But this is the first step. These 2 things happen at the same time. So one of the things you'll need to know is that when you draw a mechanism, anytime you draw a step like this, you're showing things that happen all at once. So it's not like this moves out and then that bond breaks. No, it happens all at the same time. The $60 word they like to use for that is concerted. So this step here is concerted. We're showing that both of those things happen at the same time. It's a lot to swallow all at once, but is everyone following so far? Any questions at all? Looks like you guys are taking it rather well. Well, congratulations. You've made it through the first step of your first reaction mechanism that we've really studied in earnest. And like I said, the goal is not to memorize this particular reaction. The goal is to be able to apply this to a situation, even if it involves structures you've never seen before. But I would expect you to be able to draw the mechanism out and predict the product. And we'll learn, of course, more about this in chapter 7 and chapter 8. But that's what I would suggest that you will all be aiming for. Good. Well, in the next step, let me actually point out another thing. not only is everything balanced for mass, it's also balanced for charge. And that's always a good thing to do to check to make sure that you've done everything right. The overall charge here at the beginning is 0, right? These are two neutral molecules. Well, what about over here? Here we have one species that is a plus charge and one species that is a minus charge. In other words, an overall charge of, again, 0. So that's a nice check that you can make, remembering that things would be balanced for charge as well as for mass. Anyway, in the next step, I think you can already see what's going to happen. We've said how in organic reactions, I think I've even given you the one-sentence summary of organic chemistry that I learned from my professor when I was in college, which is electrons flow to regions of lower electron density. And there are no exceptions to that. Whenever you have two species in solution, one of them compared to the other is going to be more electron rich and the other more electron poor. And what happens is the electron rich area of one molecule and the electron poor area of another are going to be attracted to each other like little magnets, because that's what they are. One of them is a partial minus charge, the other a partial plus charge. And then they touch and they react. Electrons will move from the electron-rich species to the electron-poor species, from the nucleophile to the electrophile. All this language you've heard from people who took organic chemistry previously, how there's 10,000 reactions and you have to memorize them all and there's nothing you can do, they lied to you. There aren't 10,000 different reactions. In a way, there's only one, and it's what I just told you. Electrons flow from regions of high electron density to low electron density. What happens in cases when a radical reaction involves two of the same elements, such as chlorine? Well, I think you'll still be able to find something about electron demand there, so that it's not a contradiction or an exception. But really, we're talking today about heterolytic processes. So we're using full arrows here, and here it's much easier to see. You know, you've got a thing with a plus charge and a thing with a minus charge. So I think you can make the argument that the rule I just said about regions of high and low electron density, I think you can still make that argument to some degree for radical reactions. In the OWL homework, it asked which carbocation is more stable. How can you tell which one is more stable? Well, that information, I mean, I don't want to just push you off with it's in the book, but I will go over that next with examples, and I will show you how you can know which of two carbocations are more stable, and we'll give definitions for everything. Okay, so in the next step, it's more of the same. Here we have an electron-rich species, and here we have an electron-poor species. They're going to be attracted like little magnets, and the electron-rich species is going to donate its electron pair towards the electron-poor species. And again, I'll remind you at the end of my class notes for chapter 6, you will find some pointers or rules so that you can have an idea of what you need to know in order to draw arrows correctly in heterolytic reaction mechanisms. So, so that's available. You might find it helpful. Good. So, yeah, and I think you can see what this is going to give us. There's now going to be a bond between this carbon and the chlorine. And there's many more than just one way to draw this. I don't know that you even necessarily need to show every single bond like this. But in any case, since we're being specific about where all the electrons are, it looks something like that. We get chloroethane. And again, you will know by how the question's phrased exactly what you need to show. And if it doesn't say specifically what you need to show, then it doesn't matter. And in that case, you maybe could draw just ClCH2CH3. So you'll get guidance from that on how the question's phrased. So it's two steps to this reaction. The first one is protonation of the pi bond, and the second step is the chloride ion adds to the carbocation. You've probably already come across this word in your reading. We say the chloride ion attacks the carbocation. I don't know why. That word's been used for probably 60 or 70 years. Certainly it long predated me. So it's a violent subject, organic chemistry. This anion attacks the carbocation. All right. Are there any questions then on those two steps? Which again, this is just one example of typical polar or heterolytic process. So here's what we'll do. Let me show you definitions and give you what you need to know about carbocation stability now. Normally we go over that later, but this way you won't have to look it up special. So carbocations can be categorized by what is attached to them. And the least stable type of carbocation is just methyl, just CH3+. That's the least stable. But what if we start now replacing those H's with alkyl groups? Let's say we replace one H with an alkyl group, and that R can be any hydrocarbon group. Well, I think you'll agree, whatever this group is, even if it's just CH3, there's a lot more electron density on. You got all those electrons in all of the carbon-hydrogen bonds as well as this carbon-carbon bond. That's a lot more electron density than you'll find in a carbon-hydrogen bond. So that's why this type of carbocation is a little bit more stable, and so we call that a primary carbocation. Primary meaning that there's one alkyl group attached. You can continue putting alkyl groups on. This is another possibility of a type of carbocation. And these two groups, R1 and R2, can be the same or different. Well, now we're putting even more electron density. Again, I want you all really to be feeling and understanding this is a carbon with a plus charge. It's lacking electron density. So the more things with electrons in them that we can attach to that carbon, the more we'll be stabilizing it, the happier we'll be making the carbocation. Because electrons are negatively charged, and they will help to stabilize this plus charge by putting more electron density around it. That's what you need to know, not just memorizing, you know, methyl primary, secondary, tertiary. You need also to understand why this is the order of stability. But this is then a secondary carbocation. And last but not least, I'm going to have to put it in over here, as you will have guessed, is if we replace all three of those hydrogens with alkyl groups. We call that a tertiary carbocation. And that's the most stable possibility, other things being equal. So if you find it helpful to put in less than signs like that, that's fine. But again, don't just memorize this. You need to understand why that is. For all I know, I might ask that. Why is a primary carbocation more stable than the methyl carbocation? I've done that in the past. And if you understand why, oh, it makes it so much easier. If you try to approach a subject like this as just memorizing a bunch of rules, you're setting yourself up for so many difficulties. And I know it's hard because people say, well, I'm not going to have to know why a secondary carbocation is more stable than primary in my job later on. And that's very true. But my contention is that there are going to be things that you are going to have to know for your job, that you're not going to be able to learn at an adequate level unless you learn to practice that in studying organic chemistry. That's probably why organic chemistry has been deemed by the powers that be to be necessary for all these other majors. So that's just my opinion. Good. So this will hopefully answer your question about the OWL assignments. And yes, I could have just had you guys look that up. But I don't mind going over that now so that you have all the definitions and you know what you need to know in order to answer that question. Does that help? So the more R groups attached, the more stable the carbocation is. Yes, and the reason, you need to know the reason for it also. Because the R groups are going to, this is off topic, but you all know when he posts the OWL grades. I'm never going to post your OWL grades on eCampus because you can always see them on OWL. But I am going to get them pretty soon when I go to calculate estimated class grades. Does more R groups make the bonds harder to break? Well, I don't think you're going to be breaking these bonds anytime soon because you've already got an electron poor carbon. So I think my one-word answer to your question is no. More R groups doesn't make the bonds harder to break. Rather, what it does is it puts more negative charge around this positively charged species, making it happier, making it more stable, as compared to something with fewer R groups attached. Good, other questions? Well, I hope everyone's registering their attendance. I don't really, I'm trying to think, do I even really want to do this? Because, well, it's fine. Let's go ahead and do this. I just have a little exercise just to, oh yes, stability. Oh yes, yeah, the more R groups, the more stable. And there's a very good reason for it, as I've said. But I just have a little exercise for you guys here. I can maybe use the time to get set up for the rest of it. But so everyone, please register your attendance. It's just free 10 out of 10 today. And in the meantime, I'm going to put you to work. So here, I'm just asking you guys to write the propagation step for this reaction. It's similar to what we did the other day, but not exactly. So I think it's good to practice that a little bit in class. So don't worry about initiation or termination. Just write the propagation step and do it like we did in class. So you need to show everything we showed in class the other day for the propagation step. While you work on that, I can't do anything because I can't get to my whiteboard. That's fine. Wait a minute. I'm not sure the clock on this computer is accurate. Well, be that as it may. And you can continue to work on that later if you'd like, maybe even come up with the initiation termination steps. But I've given the answer here, and I'll upload this later to eCampus so you can get that whenever you like. But if you compare to what we did with methane and bromine, the first step involved a halogen radical using its one electron along with one of the two electrons in the carbon-hydrogen bond shown, you know, whichever one changes to a carbon-halogen bond. That's how you know which one to take. And these two come together to form a bond between, wait a minute. Oh yeah, there's your HCl that we just made. And the other electron that used to be in the carbon-hydrogen bond goes onto the carbon and makes an alkyl radical or a carbon radical. And then this radical in turn reacts with whatever halogen you're given. If you're given Cl2, you'll use Cl2. If Br2, you'll use Br2. And this electron combines with, again, one of the electrons in the halogen-halogen bond. That bond is relatively weak and easy to break. The remaining electron goes onto the other halogen atom to give back another halogen radical. So in the propagation, you should always be using up a halogen radical and then regenerating it. So there's always two steps involved. And again, as I said down here, some people just want to show these coming together and say you get this radical in HCl and then redraw this radical reacting with the halogen. In other words, instead of showing it in a linear fashion like this, Some students like to show it in two discrete steps, which it is still 2 discrete steps, but they want to redraw this one and show that reacting with the halogen to form these 2 species. That's fine. I have no preference in the matter. I don't care if you draw it all linearly like this and then sort of reuse this structure to get to the second set of structures, or if you want to redraw your alkyl radical and do it that way, totally fine. I have no preference either way. Use whichever works better for you. So this will be on eCampus for you to look at later. Good. Isn't there an H missing on the last CL? Can you elaborate? Let's go over this again. So let's see. Isn't there an H missing? No, this is an unpaired electron. This is a chlorine atom. I'll go over the whole thing again. I'll elaborate fully on absolutely everything. This here is, this one fishhook arrow is coming from that electron. And it shows that this unpaired electron is going to come in between and react with 1 electron in this carbon-hydrogen bond. And that's what this half arrow is showing. So you're showing these 2 meeting together. The way you know that they need to meet together is because they're single electrons, and we need 2 electrons in order to make a bond. So this is how we did it in class the other day with methane and bromine, and this is how we'll do it here. It's not complete then. This is not the whole reaction. No, this is just the propagation step. You were asked to write just the propagation step. I think, I hope so. Write the complete propagation step. So yeah, it depends what it's asking you to show. You might be asked to show the whole thing, or you might just have to show the propagation step. No, it's fine. You're totally fine. Anyway, there's still 1 electron remaining in this, and I did the best I can. I'm kind of limited with ChemDraw. I really would have liked to show that arrow pointing exactly at this carbon, but I did the best I could. So this remaining half arrow shows that the remaining electron in the CH bond goes onto that carbon, and we make a radical. And then in the next step, we show this single electron reacting with 1 of the 2 electrons in the halogen molecule, and you see those 2 half arrows coming together to form a bond between carbon and chlorine. That's how we get here. Meanwhile, the remaining electron in that bond just goes onto the chlorine atom. And so you get that halogen radical. And that will now go find another alkane molecule, of which there's plenty, right? There's a large excess of alkane, so you're never going to run out. And it will react again and make another radical, which finds another alkane molecule, and so forth. The chain continues. Now, this will keep happening until you run out of your halogen, of your Cl2 or Br2, which you will eventually. And that's when the reaction terminates. Good. Can you show us what the termination step would be for this example? I could, but time is somewhat limited. I would say if you want me to show you actually, here's the best thing to do. See if you guys can come up with the initiation and termination steps. Remember, there's probably going to be like 3 different termination steps, any one of which would be acceptable. But that would not be, I really don't want to just give it to you. I mean, I also don't want to be frustrating, and I want to be as helpful as I possibly can. But I would say that would not be wasted time. See if you can work out what the initiation and termination steps look like. And then if you want to talk about that in office hours tomorrow or Saturday, that would be an excellent use of that time. But I think you'll get more out of it if you try to figure it out on your own. So what you do is go back to what we did the other day. Wherever you used CH4, use a cyclopentane. And wherever you used Cl2, use a chlorine molecule. Wherever you used a bromine radical, you'll use a chlorine radical. And just replace everything and see what it looks like, and it should work out. Good. So now I'm trying to figure out, that says 1121. Oh, so does my cell phone. Okay. I was a little confused then. Good. So the rest of this chapter really discusses things that really you covered in Gen Chem. But, and I'm not going to have time to go over every single one of them in detail. but I think it's good to review whatever we have time to review, and especially to start getting used to and reminding ourselves of the whole idea of energy diagrams. So, and like I said, we'll have more to say about both of those things. Chapter 6 and Chapter 7 are sort of like one big thing to me. So I'll eventually get to whatever we have time for. But let's see, so we didn't need to submit that anywhere, just practice on our own. Yes, you only needed to register your attendance. So if you still haven't, please do so. But if you do, it's a free 10 out of 10 today. Good. So what are some things that we need to say about reaction energy, about energy diagrams, and all that sort of thing? And I touched on a lot of these topics before. You will recall that whether a reaction even is spontaneous as written, which you can't just tell by looking at the balanced equation, that's determined by this Gibbs energy. And I know you loved the Gibbs equation. Delta G is delta H minus T delta S. And we could still do word problems involving that equation. I'm not real excited about doing it, and my guess is you guys are even less excited, which I don't blame you. But it is all still there, and we could if we wanted to. And even if we don't do problems like that, there's a lot we can learn just from looking at that equation. For example, you might recall Gibbs energy, well, that's going to be either positive or negative. And if delta G is positive, we say the reaction is endergonic, right? So all of these words are in your textbook, and they're all defined. And anyway, you covered them in Gen Chem. But what that means, if a reaction is a positive delta G, is it is not spontaneous as written. Only the reverse reaction is spontaneous. Meanwhile, if delta G is negative, then you've got an exergonic process. That one is spontaneous as written. And what decides that for us is these two other terms. Delta H is the energy of heat transfer. And that has the same sign convention. That's how I always like to think about it, as delta G. And you can tell that because they both are like positive terms here. It's delta G and delta H. There's no negative with those. So if delta H is negative, we say the reaction is exothermic. It releases energy in the form of heat. If delta H is positive, then it's endothermic, and it requires heat input in order to go forward. And you can have spontaneous reactions of both types. So I like to remember that delta G and delta H have the same sign convention, negative good, positive bad. And you can tell that just by looking at the equation, because they have the same signs in the equation. Meanwhile, in front of this other term, notice that pesky minus sign. That means delta S, the energy of disorder, has the opposite sign convention, right? So for delta S, it's positive good, negative bad. So a positive delta S means it's entropically favorable. A negative delta S term means it's entropically unfavorable. And so entropically favorable means disorder is increasing. Unfavorable means disorder is decreasing over the course of the process. And again, it could be either in any given reaction. So the reason that I'm saying all this is just to bring all this to mind and help you to remember going over all of these things and what all this meant. In the end, it's these two terms together that come together to determine delta G. And probably one of the more important things I could tell you is to remember that you cannot tell whether a reaction has a positive or negative delta G or a positive or negative delta H just by looking at the balanced equation. So if you're thinking you missed something, that you don't know that, because you're not missing anything. So just by looking at a balanced equation, you can't tell if it's spontaneous or not, if it's exergonic or endergonic. Same thing with delta H. There's no way you can tell just by looking at a balanced reaction equation whether it releases heat or requires heat to go forward. So that I think is a good thing to grab hold on to, because in my experience, a lot of students are wondering, am I supposed to know that? No, you can't know that unless you're given data. Now, delta S is a little bit different. You usually can make a pretty good guess as to whether a reaction has a positive or negative delta S just by looking at the balanced equation. Even the reaction we just did. You've got ethylene reacting with HCl, and you get chloroethane. Well, this looks to me like I've got 2 particles bouncing around on this side for every 1 particle bouncing around on this side. This looks to me like we have more disorder, more things bouncing around when we started than we do when we ended. So it looks to me like the disorder is going to be less after the reaction is over than when we started. It looks to me like the disorder is decreasing. And while we certainly couldn't come up with a number, I think it's reasonable to guess that delta S is negative for this reaction, that it's entropically disfavored. Meanwhile, the reverse reaction, if you could do the reverse reaction, actually you can, we'll learn about that eventually. In the reverse process, you wind up with more molecules than you started with. So I would expect in the reverse direction, I would expect delta S to be positive. So I don't know about numbers. I wouldn't expect anyone to be able to come up with a number, but you can usually make a very good educated guess as to the sign of delta S just by looking at a balanced equation. A couple other things that you can't know just by looking at a balanced equation. One of them is how fast the reaction is. And an example of that that I like to use is the reaction of diamond, which, as you know, is an allotrope of carbon, going to graphite, which is the lowest energy allotrope of carbon. Now, this reaction, as I've written it, is spontaneous. Delta G is negative under, at room temperature and atmospheric pressure. Delta G is negative. This reaction is spontaneous. What this means is that anyone here who's wearing diamond jewelry, diamond earrings, diamond necklace, ring, whatever, it is true that as we speak, your diamond is slowly turning into graphite. But I don't think anyone needs to worry about this, because we are all going to be long since dead before there's any detectable amount of graphite in your diamond. This reaction, if I recall correctly, has a half-life on the order of hundreds of thousands of years. So it's very, very slow, but it is spontaneous. So what you need to know from this is that reaction rate and reaction energy don't necessarily correspond. And you certainly can't tell how fast a reaction is just from a balanced equation. And I think it's useful to be able to understand that there's things you cannot tell just by looking at a balanced equation. And so these are among them. I still have a minute, although I think I'll need to leave, more on intermediates and transition states. We can leave that for Friday. There's still time before the OWL assignments due, but I'll get done what I can. But I do just want to remind you what a typical reaction energy diagram looks like. Generally, on the vertical axis, you want to put some kind of energy, and it could say E or delta G or delta H. None of that's really going to change the shape of the graph. Now, in chapter 2 and 3, I think it was, we used dihedral angle over here. Normally, we use what's known as the reaction coordinate. And what that means is that as we move from the origin and away from the origin, towards the right on this horizontal axis, the reaction goes further and further to completion. So at the far left, we've just got starting materials, and at right, we've got products. So sometimes students tell me they have trouble conceptualizing reaction coordinate. So what I like to tell people is it's kind of like time. You can consider time moving from left to right. And it isn't exactly precisely correct, but it's pretty much the same thing. It works out to be the same. And next time, we'll start filling in this diagram even for the reaction we did with ethylene and HCl. And we'll learn to apply some of what we saw towards that reaction. But I am out of time. So I will see you all on Friday.